Hello, we are Expert Networks. I am Carlos Gonzalez. I primarily work as the project manager and the database manager.
I'm Katrina Nicholas Orr, and I'm the front-end developer.
I'm Giovanni Vasquez, and I was a backend developer.
I'm Justin Samuel, and I'm also a backend developer.
I'm Jitin Samuel, and I'm also a backend developer.
And our sponsor was Allison Beatty as part of Ensign. Ensign is the National Security Innovation Network, which is a network within the U.S. Department of Defense that aims to build networks of innovators that generate new solutions to national security problems. At the moment, there is no good public tool for quickly identifying experts in a field with the ability to organize and filter them. Due to the absence of this tool, there can be lengthy delays when trying to gather experts to solve national security problems. These delays can be further extended to any organization that needs to consult experts when attempting to solve any significant problems. Now, there are many powerful tools that are able to retrieve a large collection of works in certain topics, such as OpenAlex. However, there's no easy way to retrieve a collection of experts. Most tools focus on finding a single expert by retrieving their profile. As for the tools that are able to somewhat retrieve a list of experts in the field, the author metrics are usually limited to whatever database they are pulling from, and this is subject to the shortcomings associating with that dataset. Furthermore, these results have no ability to be sorted or filtered inside the tool itself.
Some of the impacts of our project include it allows organizations who are seeking to consult experts in certain topics to easily identify them. As mentioned before, this can include finding experts to solve matters of national security like cybersecurity, general environmental protection, or economic development, to name a few. Another impact of our project is allowing headhunters to quickly and easily identify experienced candidates for any job positions. Students seeking guidance in their research papers or projects can easily identify relevant experts near them that have investigated similar topics. Students can contact experts through the official website of the institution, as most affiliated authors will have their email present in the institution's website. Finally, our website can enhance the representation of underrepresented groups by featuring experts from diverse regions across the globe. This approach allows users to discover experts from less represented countries, fostering opportunities to broaden their networks and collaborate on future research endeavors.
For project goals and objectives, our main goal is to create a public tool that quickly and easily identifies, filters, and sorts experts from various academic fields from all over the world. To fulfill our goals, we must create filters for field of study, geographic regions, and institutions. First, the filters for this field of study and geographic regions have various levels, starting from very broad to very specific. This ordering allows users from various backgrounds to access experts based on their needs, recognizing that not all users are familiar with the most specific topics. Furthermore, we must ensure that the website returns results relatively quickly. Ideally, we want it under 1 minute. Long search times can deter more casual users from using our application. To allow users to construct their tables and networks to their desires, we must also allow for fast recording sorting to show that the user's results of their selection as soon as they choose it. Once users have constructed their tables, we offer users a variety of download options for storage and further analysis. And finally, we recognize that not all users are familiar with the metrics used to quantify the work of research experts. So therefore, we allow users to hover over the column names to view a description of each column's meaning, such as like a tooltip.
Our general approach was to use a MERN stack because of its ability to create entire websites using only JavaScript rather than having to use multiple other languages. It's very scalable, it has excellent community support. Node.js has a non-blocking asynchronous nature, which we leverage to perform operations such as data fetching, processing, and API requests without slowing down the server, and our team was already familiar with the MERN stack. We used a modular architecture throughout the entire application to ensure the common components were grouped together for improved code management and readability. Furthermore, we also use RESTful API structure to allow for stateless communication between the servers for improved software maintenance.
Instead of using MongoDB as typically used in MERN stacks, we opted to use MySQL due to its fast read, powerful joins, and ability to structure relational data. In addition to MySQL, we leveraged Redis's order one search time complexity to cache frequently accessed large records, improve batch searching times, and improve download times across the globe. We use Sequelize to map models directly to database tables. After creating these models, we use Sequelize for all interactions with the database. We opted for Sequelize because it is mature and well established, and Sequelize also has extensive documentation and community support. Finally, we use the OpenAlex dataset for all author records, as well as all records relating to fields of study, such as domains, fields, subfields, and topics. OpenAlex is a completely open source tool for indexing scholarly works. The metrics for each author are calculated from all the works associated with them in the OpenAlex dataset. Therefore, we can use only the authors for this application. We avoid common shortcomings of using single data sources because OpenAlex pulls scholarly works from a variety of sources and then calculates the author metrics. For the institution data, we use a community-driven ROR dataset, which is comprised of over 100,000 research organizations from around the world. Finally, we use the UN M49 for defining associations between different geographic regions to ensure that the definitions are easily understood by people from around the world. As for project implementation, we created a separate table for each level of the fields of study and geographic regions, institutions, and authors. The structure of the author data in the OpenAlex dataset allows for many authors to have many topics. Therefore, we created an intermediary table, author topics, to achieve a many-to-many relationship between authors and topics.
We created a route for each of the major functionalities of the program: downloads, searches, CSV importing, and generation of the drop-down menus. Each of these routes have sub-routes that are handled by controller files. DigitalOcean has security restrictions that prevent CSV data from directly being read into the databases. Therefore, we use a CSV parser to read in the CSV data into the databases from the OpenAlex and ROR datasets.
The front end of the application uses React to create a dynamic, responsive user interface, leveraging components and the virtual DOM for fast interactions. Bootstrap simplifies styling and ensures responsiveness, while custom CSS aligns the look with our desired theme. React hooks like useState and useEffect manage local state and enables asynchronous data fetching for dropdowns and search functions, which uses RESTful queries to retrieve data without page reloads. Dropdowns dynamically filter based on user input, maintain sync through controlled components for a straightforward user experience.
When conducting searches, the front end sends requests to the backend where searches occur in batches of 100 to prevent server timeouts. Once the limit specified by the user is reached, results are displayed on the website. We leverage the order one time complexity mentioned earlier to search a batch, cache results, and then fetch the cache results in the next iteration and append the next 100 authors from the database. Search results that are smaller than 5,000 records are only cached for 10 minutes, mainly to avoid having to search for the database again when obtaining the results for the download. However, results that are larger than 5,000 are cached permanently to improve future search times since a search of 5,000 would already take longer than a minute, which is not optimal from our website.
To get a sense of what our design was going to look like, we created an initial design in Figma and sent it over to our sponsor for approval. Once we had the initial design approved, we implemented any feedback or changes requested. Throughout each new feature added, we made sure to update our sponsor and get approval as needed. After we got our application prototype deployed, our sponsor was able to monitor changes as we implemented features. Any notable feedback and ideas were conveyed during our weekly meetings where we noted them for development.
Once we had a good idea what the performance constraints for our project would be, we tested the functions by executing routes using Postman. We used the query parameter section of Postman to test different inputs to ensure that our functions were executed as intended. Queries were tested on Workbench to ensure the correct data was returned. Once queries were tested on Workbench, we converted the smaller queries to SQLized functions. Logging was enabled in the SQLized connection to ensure that SQLized functions log their raw SQL counterpart. Once we had tested the queries and the individual function, we compiled the React scripts to test the functionality of the backend when used from the front end. We used the network tab when inspecting the website to see how long the fetch request took to execute. Once everything was tested locally, we deployed the application to the prototype to test it on the DigitalOcean server. To preserve the integrity of the code, we assigned each task a branch in Git to ensure that changes and errors were contained to just the branch. After conducting the testing procedure just mentioned, we merged back to the main working branch of the project.
And now we'll take a quick look at the application as it stands right now, just for a quick demo. We will select from the first drop-down menu, we'll select physical sciences. Then we'll take a look at computer science and the subfield artificial intelligence. And we'll take a look at it specifically in the US. and then we'll set a limit of 500 people. And once you hit search right here, you can see that we get these results right here, 100 records per page. And all the way at the bottom, you can see where you can switch the pages. And all the way here at the top, we'll go ahead and sort them by citations in descending order. And then you can hover over these results to get these descriptions. Thank you for your time.